Can you see my slide?
Yeah, I can see, and now you can show the slide share.
Okay.
Okay, Prof, shall I start?
Yes.
Okay, good morning, everyone. Welcome to our third session. And today we will learn about the XRD analysis, how to do the characterization and all theoretical and practical. Prof will share. So today our facilitator, all of you know him already because Prof supporting us last few years, couple of years. So I just introduced Prof working in material science department, Faculty of Science and Technology at University Kawangsaan, Malaysia. So please help me to welcome our today's facilitator, Professor Chia.
Thank you, Mr. Sapia. So good morning, ladies and gentlemen. So this is Chia, as introduced by Mr. Sharas Chaburi. So thanks again for inviting me to share my knowledge about XRD. So the title of my the seminar today is X-ray diffractions, a key tool for understanding material structures. And
Prof, we can't hear you.
I can hear you. Can you try again?
Now can hear, Prof. Yeah.
Okay, yeah. So I check. So is it better now? Okay. So the title about XRD, key tools for understanding material structures and properties. So I'm from Material Science Program, UKM. So it's also known as National University of Malaysia. So I break down my lecture today into several topics. So I have 3 hours, 3.5 hours, I think 3 to 4 hours. So I don't want to really burden the students. So I make it slowly. So the topic basically will cover introductions, so more general, so at least students understand what is XRD. So why you need to use XRD? Some students may not need to use, and some students they may need. So it really depends on what kind of study you're doing. So I'll explain a little bit on the basic principles behind of XRD, and also examples of applications. Then we'll go further in depth into how X-ray, why X-ray is chosen as the photon to extract the informations about crystallinity, crystal structures from crystalline materials. Okay, then I will explain also Bragg's law, the theory behind of XRD. This is the most important theories behind it. So why X-ray is chosen? Then how can we calculate crystal informations using X-ray based on the wavelength of the X-ray that you choose? Okay, so in what kind of interference, okay, when X-ray passing or shine onto crystalline material, and from here you will know that why amorphous sample or amorphous material is not suitable to be analyzed using XRD. Only crystalline material is suitable. So here I will explain further. Then another important parts would be the data collections and also data interpretations. So I noticed that quite a lot of students actually they do not have how to say not really trained to perform properly in terms of the plotting, XRD, the spectrum plotting, and also data interpretations to obtain maximum information behind that you can get from the XRD spectrum. So I'll introduce you a couple of ways, what kind of software you can use, mainly freeware, free software or free website or free information you can obtain from the internet. So I will do a little bit of demo. So at least you, without using licensed software, you also can perform the same thing. Okay. Then last one, I will try to relate or try to provide you informations based on my own experience of doing research in Malaysia, in UKM. So I will give you a couple of examples of my previous projects, and I'll explain to you why I use XRD. My students, okay, or my researcher in the lab use XRD, and what kind of material we are synthesizing, and why XRD is important for our materials, and what kind of information that we can extract or we have extracted from the sample. So how can we use it to do discussions for our thesis and also manuscript for publications? Okay, that would be maybe I think 4 to 5 different studies. So I think this is important because no point to concentrate on the basic or principle. I think when you know or understand briefly about the basic or general idea what is XRD, you should try to relate with the real applications. So this is the purpose of I've tried to include several examples to you. Then lastly would be the conclusion. So basically not conclusion, just wrap up, okay, to tell you why XRD is so important. Okay, so XRD is a very popular, I would say one of the widely used scientific instruments, especially in material science, in engineering, okay, in geology, in pharmaceutical, you see here, forensic, okay, environmental also, materials, okay, materials, nano composites, okay, polymer also. Don't be surprised, polymer study use a lot of XRD, and also material science here. So example of forensics. So because you can use XRD to determine the phase, what kind of phases presented in your materials. So you know that where is the where could be the possible sources of that materials. Then pharmaceutical drugs, okay, tablets. You want to know the composition of it, what kind of phases of the ingredient in the sample. Then environmental, for example, geology. So you have rocks and clear minerals. So you want to know what kind of what is the compositions, what are the crystal phases, okay, in that sample. So here are examples of couple example of the photo about rock or mineral sample. So you have tablets. Then for plastics, polymer. So I mentioned just now, in polymer industry, XRD is one of the popular instruments because by using XRD, you will have the chance to determine the degree of crystallinity of polymer. So you know that high density polyethylene, low density polyethylene will have completely different properties in terms of strength and so the flexibility. So you use XRD to know the degree of crystallinity of the polymer. Okay, then as well as in metallurgy, okay, in metal and alloy, you need also XRD. So this is a little bit of the schematic of how the arrangement of the XRD components for you to able to extract the X-ray diffractions. Okay, so what is diffractions? So diffractions basically we observe it in our daily life. So one very common example is polycarbonate polymer. This is transparent, coated with a couple of layers. One of the important layers is an aluminum layer. So laser, when you want to try to store information on the disk, the laser will kind of engrave. It will provide, it will shine on the layer of the aluminum and to convert it into aluminum oxide. So this is the storage, how you introduce the binary data 1 and 0 onto the disk, so that when the encoder read the informations, then you have the signal. Okay, so why you can see this kind of diffractions phenomena is because of the dimensions of the pit and also the length, okay, is in the within the wavelength of visible light. So visible light is around 400 to 800 nanometers. So these dimensions, okay, the repeating pattern on the disc is more or less within the visible light region. So you can easily see the diffractions, and you see some rainbow color. So this is one good examples of diffractions. And not only light, okay, this is also another examples of light diffractions when you have an obstacle or a small gap. So it will deflect, okay, diffraction, and also water diffraction also. Diffraction is not something new. Okay, so we have been observing it for many years, but maybe you have no ideas what is that. Okay, so this is where the XRD step in and provide the solutions for us to check the crystallinity of materials. So what kind of applications that you can use? So for example, I showed you just now mineral identifications. So you can use you can identify, and also you can also quantify, okay, compositions in minerals using XRD. So pharmaceutical, okay, you can determine the purity, okay, or active ingredients in the drugs, because in the drug you have a lot of different compositions. Then polymer, I told you just now, we study crystallinity, okay, because degree of crystallinity determine the final mechanical properties of polymer. Then environmental science, so rocks, sediment, okay, sediments provide valuable information about geology, environmental conditions. Then I think the last but not least would be the material science, okay, because material science students always study microstructures of metal. So different microstructures, different crystallinity, okay, or different compositions or different phases of the crystals will determine the final properties. For example, thermal stability as well. So last one, semiconductors. So this is one of the very popular industry at the moment. So because of the various potential applications in market. So yep. So, and also what kind of information actually you can extract from XRD? Number one, you will able to know the crystal structures. So you know different crystal means a material with high crystalline material, means the atom is arranged in order, okay, with repeating patterns. So the atom is not like amorphous. Amorphous is the atoms are aligned randomly, okay. So crystalline materials, you can extract information such as lattice parameter, okay, the cell volume, the space group, okay, and the d-spacing as well. So this kind of information will have you can use this information to correlate with compare with the library or the database. So from there, you know what kind of materials that you're dealing with. Then also phase identification, okay, and also analysis. So different crystal structures, okay, same atom, okay, same atomic compositions will also have different phases of arrangement. Because, for example, I give one example: titanium dioxide. You have three major phases: anatase, rutile, and also anatase, rutile, and also another one. What is it? I forgot. Okay, so that three phases will have different properties. For instance, like photocatalysis performance. So by using XRD, you have a chance to know the what kind of crystal phases of your materials. And using XRD, you're able to do quantitative analysis. So, but it's not a straightforward method for you to enable to determine the compositions. You need to carry out calibrations from known sample with known compositions. Then you can do so. Okay, it's not that straightforward. Is if you compare with XRF, X-ray fluorescence. X-ray fluorescence, you are able to know the percentage of the compositions, but XRD is an indirect method. But it's still one of the potential or suitable method for you to use if you want to check compositions, okay, compositions of your materials. Then another powerful functions of XRD is you able to know or to calculate how much residual of stress and strain inside a sample. Okay, because you know that when materials exposed to stress or exposed to the environment, let's say heat or stress, impact or tensions, Sometimes you may not able to see failure from the outside, okay, from the appearance. Okay, you assume that the material is still good enough, but bear in mind some defects may already happen inside the arrangement of atom that you are not able to see using naked eyes, but using XRD you're able to check how much residual of stress and strain inside your sample. This is very important in construction or high performance, for instance, like load bearing applications like alloy, steel. Okay, this is widely used in material study. If I have time, I will cover a little bit on this part because yeah, you need some calculations, okay, on data interpretations from the XRD diagram. Then XRD has been used a lot in thin film and also coating. Okay, so using XRD, you're able to see thickness. Okay, indirectly you can calculate how much thickness of your coating, then also compositions. Okay, and with that you're able to optimize the coating performance. Then determining purities. So if you know the compositions, then if you have some impurities, then you're able to detect using XRD. And also studying crystal defects. Okay, so arrangement of crystals, atom in crystalline materials will have some defects. Okay, when exposed to certain conditions. So with that, you can also monitor it or characterize it using XRD. Okay, so a little bit of crystalline material, polycrystalline and amorphous. So what is that? So we know crystalline material is a material with atoms nicely arranged in order. So we have repeating patterns of the arrangement. Then also we also know that amorphous, okay, amorphous material, whereby the atoms are randomly aligned, okay, arranged. There's no any fixed or repeating patterns. And one term that we also use is polycrystalline. So it means that material contains many crystals. Okay, so this is one crystal, this is another crystal. So in between crystal and crystal, the atoms are arranged in different order. So this is polycrystalline material. So most of the material that we're dealing, I would say most of the material we're dealing in our daily life, they are polycrystalline or amorphous. Okay, so means that if you want to get 100% crystalline material, I'm not sure whether you have that material in your experience, but most of the time we are dealing with polycrystalline material. For example, like this one. This is a microstructures optical micrograph or microscope image of metal alloy. Okay, metal alloy. So you can see you have after this after polishing, you have the sample specimen, the alloy specimen, you do grinding, then you do polishing, then you do etching. Okay, etching for you to see the grain boundaries. So you can see the specimen actually made of many crystals. Okay, this is the grain, or another term we use is grain. Okay, or we can say it's a crystal. So you have many crystals actually combined together to produce the products. So this is also glass crystals, okay, under optical microscope. So these are crystal, okay, but this material is a polycrystalline material. You have many crystals, okay, many crystals that combine and produce the final material. So this is polycrystalline material, okay. So yep, so I think basically I covered just now. So amorphous material, one of the good example of amorphous material is glass. Okay, glass. Why glass is transparent? So mainly because of the amorphous nature of the silicon dioxide. Okay, so why I put this? I explained this at the beginning because I just wanted to emphasize here. XRD is suitable for crystalline or polycrystalline material, not amorphous. Okay, because amorphous material will not deflect light. So this is one example, the glass and also quartz. So they have the same chemical compositions, silicon and oxygen, but because of the arrangement of these two atoms in the structures, in glass they are amorphous, so it makes glass transparent. Okay, and also quartz. Why quartz is stronger? Because of the crystalline arrangement of the silicon and oxygen atoms. So I think okay, I'll skip this one. So let's move on to the theory of XRD. So this is one examples of the instruments of XRD. It's done by Brooker. Got it from the website. So you can see here you have a X-ray source. Then you have a sample holder here. Okay, and also the detector. So normally the configuration is in this way, but of course you have many other configurations to obtain different information from your sample. But the most conventional way or most widely used method is something like this. Okay, so I will just cover measurement in this way rather than other types of configurations for this lecture. Okay, so when you have as I told just now in the first or second slide, so when wave, whether it's light or water, bend around or made stop by an obstacle or a small gap, then it will spread out. Okay, then it will be spread out, and after that diffraction will happen. Okay, so including sound, water, okay, water wave, and also electromagnetic like light, okay, or X-ray. So when you have the electron, okay, so the X-rays shine on the sample. This is crystalline material. Then diffraction will occur. Okay, diffraction will occur. So the signal, the X-ray diffracted, okay, diffracted is consistent actually with the wavelength of the X-ray and also the arrangement parameter of the atom in your materials. Okay, I'll explain further later how can we extract the crystal parameter from the diffractions. Okay, so a little bit of introductions. Go back again about the crystalline material. So just want to emphasize here, we have three simple crystal structures: simple cubic, body center cubic, face center cubic. Okay, so simple cubic, basically you have 8 atoms arranged into a cubic form. Then for body center cubic, you have an additional atom in the middle, okay, center of the cubic. Then for face center cubic, each face, okay, each face you have 6 faces. Then each face will have an atom sitting in the middle. Okay, this is face center cubic. Why this is important? Because don't be confused. Not actually in the schematic we always draw something like this. Then students will confuse that all materials should be arranged in this way, but that is not the case. Most of the time we will have different types of crystals arrangement structures, because bear in mind in the center you have empty space. For instance, like this one, you have empty space there. Actually, atom will sit located inside. That determined by the what type of the element that you're dealing with. Sometimes if it's allowed, if the condition allowed, impurities on other atoms may have a chance to sit inside. Okay, so that will lead you to different crystal structures. Okay, example like halide, salt that we are eating, sodium chloride. Okay, it's face center cubic structures. Okay, so and another good example when you are talking about crystal structures is carbon. So same element but different arrangement, okay, different crystal structures leads you to completely different properties of final materials. So for example, graphite is carbon, it's made of carbon, but the arrangement in hexagonal plane 2D structures with a stacking of different layer of the graphene, then is graphite. Okay, but if the carbon atoms are arranged in tetrahedral arrangement, that leads you to diamond. But for silicon carbide, okay, then this is silicon carbide. Okay, I would say it's a fake diamond. The arrangement is slightly different compared to diamond, but the performance is not comparable. Of course, the hardness of diamonds would be the best in this case. So two examples here, graphite and diamond. Same chemical compositions, 100% carbon. So for diamond, the diffraction pattern is different as compared to graphite. So here, you would, from this example, then you know that how to differentiate carbon, that is graphite or diamond, first from the appearance. Second, you can use XRD, okay, to know, or you can check which one is whether this is a real diamond or not. Then you can actually run using XRD. Then you know that it is not, it's a fake one. Okay, so besides the diffraction pattern difference, there are difference in terms of between graphite and also diamond. The appearance is also different. Okay, so so no same chemical compositions, different arrangement will lead you will give you different appearance and also different color in terms of finer materials. Okay, so why X-ray is chosen? Okay, why X-ray is chosen but not visible light or UV light? Because they are all electromagnetic waves. Okay, so but in XRD, X-ray is the laser source, mainly because of the wavelength of X-ray. So this is electromagnetic spectrum. So X-ray is here. Okay, X-ray is here. X-ray, soft X-ray. X-ray is at this region. So visible, ultraviolet, UV light, some visible light that we can see. Then infrared. Okay, infrared, longer wavelength. Then you have microwave and also radio wave. Okay, so in XRD, X-ray is chosen. Okay, why? Because the wavelength of wavelength of X-ray is ranging from 0.01 to 10 nanometer, and this is consistent with the distance between atom and atom in materials. So same like the compact disc that I showed you just now of the CD. Why we can see the diffractions and like rainbow color, because of the pit. Okay, the pit, the pattern crafted on the surface of the aluminium layer. The distance between the pit is consistent with the wavelength of visible light. So in this case, X-ray, the wavelength, one wavelength of wavelength of X-ray is fall in the region in between the atomic distance in material. So here is an example. So distance between atomic nuclei in solid is around 4 angstrom, which is 0.4 nanometers. So this 0.4 nanometer is within the wavelength of X-ray. Okay, that's the reason why X-ray is chosen for XRD. So this is the range. Okay, so I think I will skip this one. So this is where, okay, this is X-ray. Okay, 0.01 to 10 nanometer. Okay, so we are obtaining information from at the atomic level. Okay, like FTIR, Raman, UEVs, they are at molecular level. Okay, molecular level. So under microscope, okay, we can see human cell, protozoa. That's why we use visible light. So what kind of electromagnetic the photon source that we use is determined by the dimension of the specimen that you are dealing with. So like we use optical microscope. Why? Because we can see. So we using visible light, we can only extract information from at more or less the same region of the wavelength of the light. So if you go down, okay, we use FTIR, we use UV, then you will see at molecular level. So if you further go down, shorter wavelength of the electromagnetic wave, like X-ray, then you're able to see atom. You can able to generate information from at atomic level. Okay, if you want, you can go even further down. Okay, but you need to change the electromagnetic wave source. Okay, so when electromagnetic wave, for example, X-ray, okay, made with single particle, then it will be scattered. Okay, it will be scattered. So if it made with a crystalline solid material, okay, since the atoms are orderly aligned, then you have diffractions. So XRD capture the pattern of diffractions at different angle, okay, different angle from your materials. Then from there, the data will be captured and interpreted, and it tells you how the atoms are arranged in your materials. Okay, that is a very basic principle. Okay, so yep. So before that, let me briefly explain what is a unit cell, what is a lattice. Okay, what is lattice? What is lattice parameter? So the same example, sodium chloride, the salt I told you just now. Sodium chloride is a FCC, phase center cubic arrangement. So unit cell means the simplest, okay, the simplest arrangement cubic of your material. This is one unit cell. Okay, lattice. Okay, lattice is the distance between plane and plane. That is lattice. Okay, so in crystalline material, we always we need to actually name the lattice and lattice using mirror index. So for example, like this one. So you have 001. 001 is this plane, crystal plane. So mean you're talking about arrangement of the atom at this plane. 100 at this plane. Okay, 010 is at this plane. So this is, you can draw a little bit, because this is X, this is Y, and this is the Z. So 1 was X, Y, Z. 1 means the plane is sitting at the Z axis. Okay, 100, this is X. So the plane is sitting at this axis. Same goes to Y, because this is Y. Okay, this is Y. So it's crossing the Y. So if you have 101, means that X and Z. Okay, so it's crossing, this is Z, this is Z, this is X. There is no Y. Okay, so it's a plane, something like this. If 110 means it is crossing X and Y. Okay, X and Y. Same goes to 011. There's no X. So the crystal plane data that we always obtain from XRD, okay, this is a plane. These are the planes that the meaning of the HKL plane. So we use 101, 100, H, K, and L. H is 1, K is 0, L is 0. So this is the meaning of the mirror index. So from there, we know that this diffraction peak representing which plane in your crystal structures. Okay, so that's the whole meaning of it. Okay, and I have actually more, but quite redundant. So one example here, if you have 111, means the crystal plane actually crossing X, Y, and Z. So into a triangle plane. Okay, so what is crystal plane? What is that actually? So this is one example I obtained from one research article. So that crystal plane actually is something that you can observe under TEM, high resolution TEM. If you have experience, we always run XDM, HRTM, high resolution TEM. Then we want to see, we can estimate and measure the distance between the D. D is the D spacing between the atomic region. So this is when you can observe this kind of arrangement, means this is crystalline material. If you see something randomly aligned, something like maybe here, okay, so you know that this is amorphous area. Okay, so this D lattice, D spacing is actually the distance between plane and plane. Okay, so you can try to correlate the D spacing that you obtain from XRD with the one that you obtain from HRTM. Okay, so this is where the distance you can obtain from HRTM. Same goes like this case. In this case, tin oxide. So you can see this material is highly crystalline. Then you can see the spacing between the atomic layer. Okay, so diffraction occurs when each object in a periodic array scattered the X-ray. So means periodic array means crystalline material, and the radiation, the X-ray must experience constructive interference, okay, at different angle. Then from there you have the diffraction pattern. Okay, so atomic in a crystal form a periodic array and provide the coherent scatter as a scatterers. So from then the diffraction will happen. So this will give you the crystal, give you the diffraction peaks in XRD. So same like for example in this case. So assume that this is one atomic layer, another atomic layer. So X-ray is passing through your sample. Okay, so this is crystalline material. The atoms are orderly aligned. Okay, orderly aligned. Then when X-ray, the wavelength of the X-ray consistent with the atomic distance, okay, the parameter of your crystalline material, then it will reflected, okay, because this is crystalline material. So the reflections will be consistent at each layer of your specimen. Then as specific angle refraction happen, then if the reflected X-ray is in phase, okay, in phase with the consecutive layer at the bottom of your sample, then you have the constructive interference. Then detector will detect the X-ray. Then you capture count per second. So how many count per scan? Then you will detect. You have the signal from detected by the detector. Okay, so I'll explain later. Okay, in detail. So this is the configurations of XRD. You have the X-ray tube, your samples holder, and the detector. So we always have 2 theta in the X-ray plot. What is that 2 theta? 2 theta is, this is a 2 theta. Okay, 1 theta and 2 theta. So this is the theta that the degree that the X-ray shine on the sample. Then when X-ray tube is rotating, detector will be also rotating to maintain the same 2 theta. Okay, so you are obtaining diffraction happen at that 2 theta. The detector will also collect diffraction at the same 2 theta. Okay, so that's why we have the y-axis of XRD result always is 2 theta. Okay, so X-ray source, the sample holder, and the detector. Let's go to X-ray generation first. Why X-ray generation is important? Because you need to know what kind of X-ray that you are dealing with. Then because different X-ray will have different wavelength. So this example of X-ray I think should be copper. Oh no, it's not mentioned here. So what kind of material that what kind of method that you use to obtain the X-ray, determine the final wavelength of the X-ray. So this is a X-ray source. Okay, the anode is here. Anode is the method that you use. Okay, it's a photoelectric effects. So when electron is excited from the tungsten electrode, strike the metal that you use, for example, like copper. So let's say I would like to produce a copper X-ray. Okay, then this material will be, the anode will be copper. okay, and not will be copper. So why there is X-ray produced from copper? Mainly because of excitement, because of the excitement of the electron from the inner electron level, K shell, okay, or L or M. Each of the shell will definitely have a chance to produce X-ray, but most of the time we are targeting X-ray produced from the electron from K shell. So when the electron shine, okay, strike on the copper anode, it will kick out, okay, electron at the inner shell. Then when the electron excite, okay, get escape from the K shell, then those electron from the higher energy level will actually fall down, okay, replace the empty positions, and this process will produce X-ray, okay. So if the X-ray is produced by from the process of transition of from L electron from L to K, then we call it K alpha. Okay, if the X-ray is produced because of the electron move from the L shell to K, then we call it K beta. All this process will happen at the same time. So that's why you have a spectrum of X-ray produced from copper. You can have K beta and also K alpha. A little bit of signal from other higher or orbital level, but this is the main two emissions that you obtain from the copper X-ray. Okay. Okay, so the K shell electron kick out because of the electron from the tungsten. Then electron from L, sorry, this is K, okay, electron from L shell come down, then you have K alpha. Okay, if from M, then you have K beta. So this is the complete spectrum of the copper X-ray. You can see you have copper, K alpha, and K beta. So how to make sure that the X-ray strike on your sample is with only one wavelength, means with only which means only K alpha, is you can use filter. So for copper X-ray, okay, if you use copper as a target, then you have copper X-ray. So you always can use a nickel filter to remove the K beta. Okay, so if you have without the filter, the X-ray produced from the X-ray source will have two X-ray. One is copper K alpha, another one copper K beta. After you use nickel filter, the nickel filter will absorb the copper K alpha. Then to make sure that the X-ray strike on your sample is only K alpha. Okay, so that you have only one wavelength of X-ray instead of two. Okay, so if you choose different target, let's say you want to produce, let's say molybdenum X-ray, you need to use zirconium filter. Copper X-ray, you use iron. Okay, because of the absorption coefficients of the filter that able to filter the noise, other X-ray that you don't want. Okay, so that is a little bit about X-ray. So why this topic is covered here is because sometime you may have a chance to try different types of X-ray. For example, most of the time we use copper, okay, copper X-ray, because it is most I think most conventional, commonly used. But if you have a chance to try different X-ray, you should do it, because different X-ray will have different sensitivity towards different sample. So sometimes your material may not able to obtain good results from, let's say, copper X-ray. Then maybe cobalt X-ray will give you the diffractions, okay, better diffraction. So that is something that you should try. Okay, so we explore further about what is about diffractions. So again, crystalline materials, you have arrangement nicely arranged atoms. You have the lattice, one layer, two layer, and distance between the lattice is what we call d-spacing. Okay, so this is the d-spacing. This is the first parameter that we always obtain from XRD. Okay, this is the one that you observe under HRTM. Okay, so when X-ray shine on the sample, then reflection will happen. If the angle is correct, okay, if the angle is correct, then you will have collective interference. Okay, so if you notice this layer, okay, this layer and this layer, the X-ray wave travel extra one wavelength. Okay, travel extra one wavelength to hit on the atom at the bottom layer. So this extra one wavelength is something that we know from the wavelength of X-ray that we use. So if, okay, I repeat again. Collective interference will happen, okay, when at certain angle, okay, not all angle you will have the diffractions. It really depends on the material that you choose. So if happen to be at this angle, there is collective interference between layer and layer of atom after the X-ray struck on the sample. So look at the first layer here. This atom reflect the X-ray and happen to be the distance between the bottom crystal lattice also have the same reflections. Okay, then the data collected by the detector will have collective interference. Okay, so you have the detector with that the count per scan from this angle. So what we can obtain, what we can see here is at the bottom layer, okay, the second layer of the lattice, crystal lattice, the electron actually travel one wavelength extra compared to the upper one. Okay, so we know this wavelength of the X-ray, which is copper in this case. Then we use this triangle here, okay, to calculate the d-spacing. Okay, something like this. So this is where Bragg's law came in. Okay, the Bragg's law came in. So this is a d-spacing. Okay, d-spacing. So the first layer, the first X-ray, second X-ray, and the third X-ray strike, then collective interference. So each layer will provide will reflect the X-ray and detected by the detector. So no matter how many layers of your material, the detector will still detect it. Okay. So how to calculate the d-spacing? So we know the wavelength. We know the wavelength of the X-ray. Okay. So this like this one. This is half of the wavelength. This is one wavelength. Then another layer is 1.5 of the wavelength and two wavelength. So from here, if constructive interference, then you have the signal. If destructive interference, then the signal will be lost. So that's why not all angle will have diffractions. So it's very difficult actually to get the diffraction. That's why most of the time you have only maybe 5, 6 if you're dealing with metallic oxide sample. Okay, so the AO. So let's extract this triangle. The AO is the wavelength, extra wavelength travel. Okay, extra wavelength travel. So now AO equals to OB. So 2 AO equals to 1 N wavelength. Okay, the N could be 1, 2, or 3. Doesn't matter. Okay, so we use this concept Okay, sinus theta equals to AO over the DHKL. So sine is opposite over hypotenuse. So opposite is AO, which is the wavelength of the X-ray. And this is the hypotenuse, the D spacing of the sample. So 2 DHKL times sinus theta equals to n of lambda. So n is not important in this case because n could be get rid. So from these Bragg equations, we know the wavelength, we know the 2 theta, then we can calculate the HKL. Okay, the D spacing of your materials. Okay, so let me explain it a bit further on this part. So I need to get out from the presentation mode. So I just want to make sure you understand it. So let's assume that this is your sample. Okay, this is your sample. Then this is the X-ray. Okay, the XRD instrument will scan your material at different angle, 2 theta. Okay, from lower 2 theta to higher 2 theta. You can see the wave, this 4 X-ray wave is actually is turning. Then when you have, okay, when the wave striking the atom, and if you have, for example, let me move a little bit, so like this one, go with small angle. So maybe, yeah, let me go back to the original one first. Like play around. Okay, like this one. So this is the X-ray. Okay, then the second one hit the first layer, then the third one hit the second layer, the fourth one hit the fourth layer. So this so this layer will have the X-ray affected, and they will have constructive interference. So detect by the detector at this particular angle, 2 theta. So if you have this one, so means that in real scenario, when you run the sample, actually the machine will provide X-ray at different angle. Okay, if happen to be all the X-ray wave hit atoms and give you collective interference, then you have the diffractions detected by the detector. So that's how you collect the diffractions like this. So for example, this one, from low angle, let's say from 10 to theta, the X-ray source and also detector will rotate, they increase the 2 theta. So at this 2 theta, there is diffractions. So this is count per scan. Okay, so you have one spectrum, one peak. Then at 31, you have another one. At 40 something, you have another one. So it means that throughout the scanning process, the detector will collect the count of X-ray diffracted from your sample. So this is the raw data you can obtain from XRD. Okay, so from Bragg's law, you know the wavelength, you know the 2 theta. They say, for instance, like this one, 200. Then you insert into the formula, then you know the D spacing of this 200. Okay, 200 crystals plane. Okay, so in order to obtain diffraction speed, okay, diffraction speed, it must obey, okay, it must follow the Bragg's law. Okay, so means that in this sample, sodium chloride, okay, sodium chloride, the XRD able to give you the diffractions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 major diffraction peak. Okay, so this is the raw data you got. But what does it mean is another story. So how to interpret it, then we will discuss later. Okay, so means that to obtain diffraction pattern, okay, the X-ray has to be correct, correctly choose, and the angle of the diffractions must be right. Then, in order for you to collect the diffractions. Okay, so what kind of information you can obtain from XRD initially? Okay, at the first place, most straightforward formula is the Bragg's equations. D equals to n lambda over 2 sine theta. Okay, and when we know what is D, the D spacing, and we know what is H, K, and L. HKL is this one, 2, 0, 0. H is 2, K is 0, L is 0. Then you insert all the value. Then you have the lattice parameter. So lattice parameter is this one. Okay, so you have the unit cell. I told you just now, this is unit cell. Then you have a lot of plane. Okay, 100, 111, 101. That is the plane. You have the number. Then you insert the D, HKL number. Then you know you can estimate the lattice parameter. Okay, what is the length or the dimensions of the lattice? This is lattice parameter. So there are 3 variables. Wavelength you know, theta you know. Then once you know the D, then you're able to calculate the A. Okay, the lattice parameter. So what is so important about D and lattice parameter means you can kind of confirm that the material that you synthesize is the same like what reported previously. So you are trying to do benchmarking with other study. So that is the purpose of measuring D and also D spacing and also lattice parameter. But XRD is not only that. Okay, this is just at the beginning. Okay, once when you collect the data. Okay, so what kind of other information that you can get from XRD is the structures. So you know whether FCC, phase center cubic, body center cubic, or simple cubic, or maybe other types of structures. You have SCP, okay, hexagonal, center. Okay, so then peak identifications. So you have the structures and you identify the peak. Then you know your material is amorphous or crystalline. You can estimate the degree of crystallinity of your material. Okay, you can calculate the D spacing and also lattice parameter. That what we discussed just now. You can estimate crystallite size. Okay, and you can even calculate the residual stress or strain in your sample. Okay, so I will go one by one to this. Yes.
Excuse me,
Sorry.
for
Yes.
actually next we can go for 15-minute break. Then I will back 11:15 in Malaysia time.
Sure,
then
sure.
start.
Thank you. Sure. Then later maybe if you have any student has any question, you can just ask.
Yes,
yep.
Bro.
Thank you. Thank you.
Okay. Thank you, bro. Hello, Prof.
Yes, Mr.
Yeah, you can share now.
Okay, sure. Thank you. So maybe I can share my screen because I need to do some demo. Can you hear me?
Yes, yes, Prof. We can hear
Yeah,
you
thank
and we
you.
can see.
Thank you. Thank you. Okay, so we continue. Thank you for coming back. So I prepare this slide. I try to rearrange a little bit. So just to a bit of recap. So during the analysis, X-ray tubes and those detector will also rotate at the same theta. So that's why it's a 2 theta. The name of we label it as 2 theta. Okay. So at different angle, there will be diffractions. If the Bragg's law is obeyed, okay, so it means that it must be constructive interference. So in this case, I'm not sure what is this example, but it should be some kind of like mineral. So let's say at 20 to 21, 2 theta, there's one diffractions. At around 29 to 30, there's another diffractions. And 35, another one, 40 to 45, another one, and 43 and 48, another diffractions. So this is the raw data that we got. Okay, so the HKL here, the identifications of the HKL plane is something that we do after that. Okay, when you obtain the diffractions. So yeah. So these are information that we can obtain. So the first thing is structures, then crystalline amorphous, crystallinity, the d-spacing, crystallite, and also some other, like for example, like stress and strain residuals. This is also possible. So what I want to explain, maybe not okay later, I will continue. So a bit of precautions about XRD. Let me, okay. So before you send your sample to the XRD, what you need to be aware. The first one is definitely your sample preparations. Okay, if you have a big sample that not in powder form, you should grind it into powder, and before you send your sample. So there are many video you can check, you can follow. Then the sample size is also another crucial thing. Make sure that the sample quantity is enough to cover uh, the whole sample holder in order to get good signal. Then sample alignment. This will be done by the operator, I believe. Then background corrections also. Because background, the XRD diagram obtained is always corrected with the background with the sample holder. Okay, with the sample holder that you use. So this will be conducted by the operator, but you need to check properly. You need to just double confirm with them. Then use a standard sample. The sample, the instrument need to be calibrated. Okay, using standard sample. For example, quartz is one of the most popular material standard sample to use for calibration purposes. Then radiation safety. So if you visited the lab, XRD lab, you see there's one sign there to warn you that there will be some radiations. Then also temperature and humidity. So most of the time, if possible, keep your sample in plastic bag or put in desiccator, because sometimes the sample may need to stay in the lab. Maybe you need to wait for 1 or 2 weeks, right? So the sample will when the sample get exposed to temperature or high temperature or humidity, it will change the properties. So this is something that you need to take into consideration. Okay, so this is some photo. If the sample is big in size, it's not powdery form, then make sure you grind it. Okay, you grind it using this mortar or ball mill. Okay, then fill up the whole sample holder cavity. Okay, then you need to flatten the surface. Okay, to remove excessive powder, so you have a flat surface. Okay, so yep. So just assume you have submitted your sample, you send the sample, then finally you got the XRD result, and in a file, let's say in the Excel file with the reading of intensity, CPS, and another data is the 2 theta. Okay, you have the data. So before you proceed for face identification or try to interpret the data, so I would like to emphasize here, maybe my suggestion is you should learn how to prepare good or high quality XRD diagram. Okay, you can either use Excel if you do not have the access of, like, for instance, Origin software. I think you should get this one if it's possible. Then for you to prepare a nice XRD diagram, something like this. These are diagrams that we used to do. We used to use to prepare using Excel. So you can see the difference between this one and this one. So I personally prefer this because it looks more tidy and more professional for journal publications. For presentation, I think for progress meeting, for just to share with the supervisor, I think this should be fine. But for manuscript preparations, for thesis writing, I think you need something like this. So there are many videos sharing in YouTube. So this is one of the best I noticed. So you can have a look. So not only the arrangement, but also the color used. So this should be the way. So try to practice and learn how to plot a good XRD diagram. So this is the example. So it show you how the steps, okay, how to arrange, how to plot, okay, how to label, how to do the stacking and do comparison with the library. Okay, so the first one is phase compositions, phase and composition determinations. Okay, so assume that you got the diagram already. So there are several ways of doing phase determinations. The most straightforward one definitely is you talk to the operator or technicians of the XRD instrument. They should have a computer ready or standby computer for you to use in the lab. Then you can open the diagram, XRD diagram, using the software. Example, Expert High Score or Material Studio. These are two widely used one, but this is licensed software. We do not have it, so if you have, then you can watch it and to learn how to do the interpretations. But in my case, my students used to do another way rather than use the licensed software. We will use sometime we will compare with the pattern reported in journal articles. For example, this is one article called Stability of Colloidal Iron Oxide Nanoparticle on Titania and Silica Support. So this is the article. So this studies synthesized iron oxide on titanium dioxide and silica as a support. So this is ACS publications. So in that journals, in the articles, they even emphasize, explain the methodology, okay, the characterization conditions. So this study they use cobalt K alpha, so not copper K alpha. Okay, so cobalt K alpha, the wavelength is larger compared to copper K alpha. Copper K alpha is 1.45, 1.54. So cobalt is longer, okay, longer wavelength. So even the 2 theta and also the scanning, okay, the scanning speed is also one important crucial parameter you need to play around. If the signal that you obtain is not so good, the diagram is not so good, then you should repeat the experiment using, you can ask for a slower scan rate to maximize the signal, to increase the signal to noise ratio. Okay, so these are the results plotted by the author in this study. So okay, not too bad, not so bad the plotting, but just okay, and they even included the symbol, so which one represent what kind of structures, tau, tau. Okay, so I think quite straightforward. Okay, you can easily understand. So I give you another one. So another study. So produce copper nanowire. So they also plotted in here. Okay, but I think from the first glance, I know this is from plotted using Excel. Okay, I believe this is Excel. So they just label the HKL, the plane, the crystal plane accordingly. Yeah, there's no right or wrong, but just my personal preference. I will ask my student to plot it using origin. Okay, and you see the whole discussion, they will emphasize, they will also tell you the two data. Okay, what are the peaks at which location? So you can use this journal's article, published journal article, as your reference to do the fitting. Okay, to do comparison. Then you know, okay, your sample is the same like the previous study. That is one option. Second one, you use the licensed software. If you have, then you should use that. Okay. Else, okay, or else you can do it manually. You can download, you can access reference database, okay, from JCPS, and this is licensed one, and also not easily obtained, okay. Or you can search using open database, like this one, crystallography open database COD. So this is the website. Okay, then you can download the database for your material. So from there you can do comparison. So yep, this is another one. Yep. So even, okay, this is another study. Okay, they even provide you the DCPDF number, so you can directly use that for comparisons. Okay, and but this figure has one small issue, is which is I noticed that is there are some shift in terms of two data from samples to sample. That could be some interesting information that should be discussed, but not discussed in this study. Okay, but it's not important. Okay, so let me share with you how to download the crystallography open database of your materials. Okay, of your materials. So this is the website. So let's go to the page. Okay, so this is the page. For some reason, I don't know. Okay, can you see my computer desktop? My page. You can see it. Okay, so yeah, for some reason, I don't know why it's missing here, but you can try using your computer. So there's one browse here. You're accessing COD data. You go to search, also can search. Then here there are different search functions you can use. If you have the COD ID number, you can straight away key in. But I found it hardly get it because this kind of information ID is not provided in journal article. So I will use this search engine just by key in the element. Okay, for instance, iron, then oxygens, and maybe copper, something like this. Okay, just key in whatever element that you know, okay, presented on the sample. Then you can just click send. Okay, then the system will list down all possible structures that you may have interest. Okay, I think too many is too many because of the element that I key is kind of too less maybe. But I try again. I try whether I can get, let's say, copper ferrite, for example. Let's try to check. Like this one, okay. Copper ferrite.
Yes, bro.
Okay, so perfect. So I click the CIF. Okay, I click that CIF. Then I will download the file here. Okay, so let's move this file to the folder later. I'll show you for demonstration purpose. Desktop and XRD. Then I'll label this as copper ferrite. Okay, so this is the file. Then we go to another program, which is Vesta. Okay, this is Vesta. So it's a freeware also. You can directly access. You go to here, Vesta, the website. Then there is one. Yeah, download. Okay, download. And you download whatever if you use window. you use Apple, you can download it. Then you download. Then when you open it, this will be the file, Vesta. Then you straight away go to Vesta applications. Okay, then you enter the interface. Okay, you enter the interface of Vesta. Okay, then you can open the CIF file that I download just now, the copper iron oxide, or copper ferrite. Okay. No, this is interesting. I don't know what is this. First time. Okay. So maybe I try the other one. Maybe better presentation. Let's try. Okay, this one. Okay, this is what is this? This is let me check whether I can get the name of it. Okay, I think it's here. And maximize it. Let me maximize it. Okay. Yep, this is also copper ferrite. Oh, this one. This one should close it. This one. Okay, then how to extract the HKL, the standard diffraction diagram? You can go to utilities, then go to powder diffraction pattern. Okay, then you calculate. Okay, so from here, the program will give you the standard diffraction pattern of that particular material, and you can have the table showing all the peaks. Okay, all the peaks at each two theta. Okay, at each two theta with the intensity. Okay, with the intensity of 100 means the strongest signal. Okay, the peak. So you know this 100. This is the most dominant peak at 36.1. So 36.1 is here. Okay, so this information is very useful for you. Okay, for you to do comparisons first thing, and the software directly tells you the despacing. Okay, the despacing and also the HKL. So you can use this information to plot into the XRD diagram that I showed you just now, like this one, example. So you can directly label what is what, like this one, 002, 111, 110. So that's one example. Okay, you can even do some data interpretation here. There are many tools. There are also video that you can watch. A lot of things you can do it. Like you can do Fourier synthesis. You can do geometrical. You can optimize actually the result. You can change it. Okay, so for example, you can do lattice plane. Okay, you can edit the data. You go to the unit cell. Okay, you can change it accordingly. If you want something else, you can change it. You can change the crystal arrangement. Okay, to fit your own result if you want. Okay, so I think this is more than enough for you to use it, because first thing, because this is free. Okay, second, it's already more than enough for you to use, and just to do what you want, just to identify the crystal plane, what is the intensity, what is the despacing. I think it's already more than enough, sufficient for you, just using this software. I like this because it's semi automated. So if you use licensed software, it's very established. You just key in everything, basically everything will be provided. But this one, student will need to understand what kind of material, what kind of element that he or she is using. So then from there, you download the CIF file, then you do the comparison, then you try and error. Okay, so that's one thing I think students should use this, should try. Okay, So this is an example. So I forgot which one actually, but I tried yesterday. There are different functions that you can do, because I just recently aware about this software. Okay, so this is Vesta. One example I can give you. So hang on, let me close it. Okay, I hope you understand. So first thing, once you have the diagram of XRD from your sample or of your sample, you can try to search the crystallography file from database. Then you open it using Vesta to do the interpretations. Then from there, you can do the fitting. Once you have all the informations about the HKL, the plane, the 2 theta, okay, then you can plot something like this, maybe. I don't, not here. Some people actually plot, oh yeah, I did show you just now, okay. You can even plot something like this at the bottom, okay, just to stack it so that people know where's where instead of plotting in the same column. There's also another option that you can try. Okay, so this is yeah, this is the one I mentioned just now. You can transform it. Okay, you can do the fitting. Okay, you can transform it. I try. This is shown by this video. You can draw actually. Okay, you can draw. You can draw it, this diagram and put in your thesis or presentation. Lets people know where is the plane that you're talking about. Okay, so quite kind of powerful tools. Okay, so besides using this crystallography open database, if you can access the JCPTS file, okay, JCPTS cuts, then JCPTS cut will also give you this kind of information. This is where the license software provides to you. Very simple. You just key in the JCPTS number 050566. Okay, this is zinc sulfate. Okay, zinc sulfide. Sorry, zinc sulfide. So these are the crystal, the diffractions peak should be, okay, with the intensity 100 at 28.5 2 theta, representing HKL 111. Okay, the crystal plane 111. So this is one example of JCPTS file, but sometimes you may not have the access. Okay, if you do not have, then it's good for you. You can directly use. Else, you can use the one that I suggested just now. Okay, so this is another example of JCPTS cut for cadmium tellurium selenide. So basically, they provide the same thing. Okay, they provide the same thing, just different way. Okay, just different way. Okay, if you notice, the JCPTS cut also give you the wavelength of the laser. Okay, bear in mind, okay, wavelength is also one key parameter determines the quality of the diagram that you obtain. Okay, so once when you do the all this fitting, okay, all this fitting, then you know that your material contains what kind of phase, different phases. So for example, titanium dioxide, there are 3 different phases, same chemical compositions, different crystal structures. Okay, anatase, brookite, and also rutile. So when you run XRD, then you know what kind of phases of material contained in your sample. So that is the purpose of doing all the fitting. One thing, okay, one thing is to calculate the D spacing, the lattice parameter, know the HKL, but it also allows you to identify what kind of phases, okay, what kind of crystal structure that you have. Why this is so important? Why this is important? Because different crystalline structures or different phases will give you different properties. For example, titanium dioxide. Brookite is known to be poor in terms of photocatalytic performance. To have optimum photocatalytic performance, combination of anatase and rutile is always the best. Okay, for some reason, because I think it should be because of the photocatalytic optical properties of the structures is better compared to brookite. There must be some reason. But so if you're studying, if you are in your study, you would like to you would like to know what kind of structures, crystal structure, what kind of phases is better, or what kind of phases is give you better in terms of these properties, or A properties or B properties, then XRD would be the most suitable instrument for you to analyze your sample. Okay. So intensity. Okay, one thing I forgot is the intensity. Okay, the intensity. They say this is my sample, for example. I synthesize titanium dioxide. Okay, using let's say hydrothermal method. Then I conduct a calcination process to improve the crystallinity. Then I analyze my sample using XRD, and this is the spectrum. This is the diagram I got. So the red color is rutile. So in the I think in general way, you know that rutile will be the most highest in terms of the compositions in your sample because of the intensity. Okay, so intensity indirectly or directly tells you the compositions of it. I think quite straightforward, right? If you have less, means the signal is lower. So if you have more, then the signal should be higher. Okay, so let me explain to you some examples of studies using XRD. Okay, this is one example that I think many years ago, long time ago, 13 years ago. This is a work conducted by one of my PhD student that time. Then he studied to synthesize iron oxide nanoparticle, so which is magnetite nanoparticle, using hydrothermal method. Then this is the method that he used. So using ferric salt, and also sodium hydroxide alkaline at high temperature. It promotes the growth of the iron oxide crystals. Okay, so we run XRD, and we found that this sample is not really crystalline. If you have this kind of spectrum, then you know that your sample is not really, it's not highly crystalline, but it's crystalline because you have the peak, but you have also a lot of amorphous phase. Then the student run MRI test to see how much this iron oxide can enhance the contrast of the MRI image. Then it's proven works. Okay, this is one example. So means that when you conduct an experiment or your thesis study, your lab work, then you synthesize something, you want to prove that what you aim is what you get. Okay, so you should run the XRD. Okay, so yeah, this is the same thing I just like what I showed just now. So the open database, you key in, then you have the result. Okay, then this is another example. Few years back, so we synthesized silver nanoprism, okay, using nanocellulose as a template. So these are the example, the detail of it. So we try to use the nanocellulose as the template, okay, template without using surfactant from silver nitrate salt. Okay, we add in the sodium borohydride as the reducing agent, hydrogen peroxide as the oxidizing agent. So we control the volume of the hydrogen peroxide. Then our aim is to obtain different size of the prism, of the silver prism. So without the nanocellulose, the product should be in spherical shape. Okay, it's very the product should be spherical. And also there's to be no nano size of silver because of no template. You need the surfactant actually. Okay. Then these are TM images to show that we successfully produced the silver prism. Okay. By changing the volume of the hydrogen peroxide, the shape is turns bigger. Okay, the higher the bigger. So we run UVs to check the optical properties. So yep, so we need to prove that it is silver. Okay, this is silver crystal. So we send the sample to XRD. The sample, what we did is we need to dry the sample because the sample is in colloidal form. Okay, it's in liquid form. It's well suspended because of the nanocellulose as a stabilizer. So we need to dry it. Okay, we need to dry this thing, this sample using freeze dryer. Okay, freeze dryer without using heat, so to preserve the sample. Then eventually we got the XRD spectrum. Yeah, it's quite nice, highly crystalline. Okay, and this is the spectrum I got from the Vesta software just now. Okay, it is, I would assume it's consistent. Okay, a little bit of this peak should be no, this one is also here. Okay, 45 here. So this is mainly due to the cellulose. Okay, cellulose give diffraction peak at lower 2 theta. Then the rest is silver. So the most dominant peak is this one, 38. So which is this is the one, 38. Okay, 100 intensity is the highest one. So this representing 111. Okay, 111 HK lattice plane. So the rest is not really visible. Okay, not really visible. Yeah, slightly at 50, 60 something, 65 here. You have another one. Okay. Okay, if you want, you can zoom in. Okay, then you can see even clearer. But because we do stacking, so those peak which are not dominant may not able to see clearly. Okay, so this is the list of the crystal structure that should appear in my sample if my sample is silver. Okay. So this is identification. Okay, how to identify, how to compare, to confirm that your sample is what you is something that you want to synthesize. Okay, so it's the direct comparison way of doing to identify your sample. So next one, next topic is about how to determine whether your material is crystalline or amorphous. If it is crystalline, what is the degree of crystallinity? Okay, so I give you one example here. It's from one article published in Pharmaceutical Research. So they use sucrose as a sample. Okay, then different crystallinity, then analyze using XRD. Then because sucrose is sugar, it can turn into crystal if you control it nicely. Then you can confirm or check the crystallinity using XRD. So crystalline is something like this, amorphous is like this. Okay, so very straightforward. If no sharp peak means your material is amorphous. If you have very sharp peak like this, so this is highly crystalline, and this is polycrystalline. Okay, because you have different peaks. Okay, so many peaks, so this is polycrystalline. Okay, then you can determine the lattice parameter. Okay, the D spacing, all this using the procedure that I showed you just now. Okay, so always remember, XRD is not for you to know the elemental compositions. XRD only tells you what kind of crystal that you have. If you have other impurities, for instance, like you have heavy metal impurities which are not crystalline, then you may not able to detect it. So always remember, XRD is only sensitive or can detect crystalline material. If the impurities are amorphous, then you would never have a chance to detect it. Okay, so then XRD diagram can only compare with database. Without database, you don't know what is that. Or without comparing with other study to know where is the 2 theta, what is the HKL, okay, the Miller index, this diagram is meaningless actually without doing comparisons. Okay, always bear in mind. Okay, so I give you another example. These are one study using cellulose as a material. Then they run XRD. Okay, so it starts from okay. So this is the result. One result. Okay, one diagram of XRD of nanocellulose. So this author would like to check or to estimate degree of crystallinity of the sample. So then he do the phase identifications using this one, okay, then plotted, then they know that which peak representing what, okay, what, then they do deconvolutions, okay, using origin. Okay, you can use origin and or other software that you have, or sigma plot, you can do deconvolution. So at this 2 theta, this is the crystalline peak. This is also another crystalline peak. This is crystalline peak. So and one amorphous peak. So you do deconvolution not only for crystalline but also the amorphous. Then from the software origin, for example, you can calculate the percentage of crystallinity by using these equations. The total area of crystalline peak, this one, this one, this one, and this one, okay, you sum it up, total, over the total area of the domain, means total area of crystalline plus the amorphous. Okay, so I repeat again, this is the equation for you to estimate, just estimate, rough estimations of degree of crystallinity for your sample. SC is the total area of crystalline peak, whatever crystalline peak that you obtain after you carry out the deconvolutions, okay, using the origin or whatever software you have. Then over total area of crystalline and amorphous region. That is percentage of crystallinity. And when you do the deconvolution, you should choose Gaussian function, which is I think one of the widely used function, and also another function. But what I noticed, many people use Gaussian function. So if you are interested, you can try to watch a video from YouTube. Many people actually sharing how to do deconvolutions, okay, for XRD, and also FDR and others spectrum also. Okay, so this is for crystalline or amorphous, okay, and also if it is crystalline, what is the degree of crystallinity? Okay, so XRD is also very popular and very widely used in polymer projects, okay, polymer materials. So in the market, okay, in our daily life we use a lot of plastics, okay, HDPE, low density polyethylene, okay, this is also high density polypropylene, okay, these are polyolefin or plastics that we use in our daily life. So same types of polymer with different molecular weight and different degree of crystallinity will give you completely different properties. It can be as flexible as a plastic bag, okay, or a film like this for food packaging, or as rigid as high performance materials like this one, or piping material, high performance tubing. So what makes them difference so much. This is all because of crystallinity. Okay, this is all about crystallinity. So look at this one here. This is film, like this one. Okay, you can roll it. Okay, during the processing, you can grow it at different temperature. Okay, you can process it at different temperature. Then turn out the film are behave completely different in terms of crystallinity. So I think from the first view, you know the red color sample. Okay, the red color line are highly crystalline. The blue color one is low in terms of crystallinity. Okay, so if you want, you can do the deconvolution method just now. Area under the peak, okay, and over total area including the background amorphous. That is the percentage of the degree of crystallinity. Okay, same goes to the fiber. Okay, polymer fiber. If you stretch it, okay, if you stretch it during the processing, another one just by gravity, it just fall by itself, then it can also induce crystallinity for you to get high performance fiber like this. So how to check? Okay, if you have material that you want to know, I control the processing parameter. I know that this parameter will result in different crystallinity. Then you can use XRD. Okay, then from there, you know, first thing, the black color line is highly crystalline. The red color one is amorphous. Okay, so the second information you can get is you can estimate the degree of crystallinity. Okay, so yeah, like example, how they do this polypropylene, okay, PE, polyethylene, PE, polyethylene, then high crystallinity, this one, this one, PE, 54%, and this is 23%. You see the amorphous region area is quite big. Okay, this is amorphous, the background is amorphous. The sharp peak is crystalline. Okay, you can use the same thing that I showed you just now, same equation just now. You do deconvolutions. Okay, crystalline over total area of crystalline plus amorphous, that is percentage. Okay, degree of percentage of crystallinity. So this is polyethylene, this is polypropylene. Okay, this is for polypropylene. So you can see 57%. Okay, so this one high in terms of crystallinity because they are more sharp crystalline peak. Although the background of amorphous is also big, but because you have more crystalline peak, so the degree of crystallinity is higher. So this is lower crystallinity of polypropylene. The background is very high. Okay, the amorphous area is big. Okay, so this is another example to be used for plastic or polymer. So we also conducted some study previously to isolate nanocellulose from natural fiber. So this is cellulose in micron size, and this is cellulose in nano size. So this is paper, okay? Paper made out of fiber with diameter of micron, okay? And this is paper made of cellulose in nano size diameter, something like this, okay? Then it becomes transparent because of the smaller size. So how to produce the nanocellulose? We normally use acid because acid is strong enough to dissolve the amorphous cellulose region. So whatever left is crystalline cellulose. Okay, so my student would like to check how much the crystallinity improved after conducting the acid hydrolysis process. So this is the nanocrystal, okay, under TM, and this is another crystal under AFM. So we confirm that the size is in nano. So the student run XRD, okay, then use the same method then to estimate the degree of percentage of crystallinity. Okay, then it's 81%. The before the acid hydrolysis is 45%. So it increased tremendously. So yep, this is another example. Okay, so another example also done by one of my PhD students in 2018. We produce graphene oxide. Okay, we try to produce graphene oxide from graphite. Okay, we has interest in graphene oxide because of the because of several reasons. Number one, because this is graphene, although it contains some defects, but the modulus is high, and graphene oxide is stable and well suspended in water, so it's easier for us to do modifications, and we can use it for many purposes. That's why this study actually is conducted to produce graphene oxide for glove rubber, okay, for rubber glove as a reinforced agent and to increase the puncture resistance of glove. So the students start with this chapter, this experiment during her PhD study. So conventional method of producing graphene oxide is using hammer chemical, and it takes hammer chemical is a combination of strong chemical like sulfuric acid, potassium permanganate, phosphoric acid. Those are strong oxidizing agent to oxidize the graphite into graphite oxide like this one. Okay, so you put the strong oxidants and you oxidize the graphite into graphite oxide. So to loosen up the structures. So the words loosen means destroy the crystallinity. So the stackings of the graphene layer in graphite no longer that packed because you oxidized. So the layer of the graphene oxidized, so the structure swell. Okay, so crystallinity will be destroyed. So this study actually conventional hammer method. You need to do it for 3 days, many days. Then a lot of works, time taken, actually quite time consuming. So the student proposed something faster in terms of the processing. So we use also the same chemical, but we oxidize it only up to 1 hour to 3 hours or 6 hours, not 3 days. Okay, 3 days is too long. So we loosen up the structures. Then after that, we use exfoliation. We conduct exfoliation using homogenizer. So it means we use chemical and mechanical and chemical approach to fasten the synthesis or production process. Okay, so to confirm that the graphite, okay, this is graphite flakes. Okay, graphite flakes. This is graphite flakes. The diffractions at around 26.3 to theta. The D spacing, okay, if you still remember D spacing using the Bragg's equations, okay, lambda sin theta is 0.34 nanometer. Means that the layer of graphene, okay, at carbon atom in the graphite, the starting material, the T spacing layer, lattice spacing is 0.34 nanometer. So the student conducted oxidations on the graphite flakes for different time, 15 minutes, 1 hour, 3 hours, 6 hours, and 24 hours. And this is the result she obtained. So still remember, this is the initial sharp peak of graphite flake. So means graphite flake is a highly crystalline material with very low amorphous, no amorphous, you see very low amorphous area. Just by 15 minutes of oxidation, it creates background of amorphous already. Okay, so the peak no longer as sharp as the graphite flakes. So, and when you increase the time, you notice the crystallinity intensity is dropping over time, then gone, missing. Means that this spacing, okay, of this crystal plane of the graphite flakes destroyed completely after 6 hours. Okay, after 6 hours, and leads you to one peak. Okay, leads you to one peak at around 10 or 9. Okay, 10 to 9 2 theta. Okay, so this 10 to 9 2 theta, the D spacing is 0.93. So means that when a diffraction peak shifted to lower 2 theta, it means the D spacing is bigger. Okay, bigger D spacing. I think from the equation, if you check back the equation, the larger the 2 theta, okay, the larger the 2 theta, the smaller the 2 theta, means the larger the D spacing. So this result further proven that the lattice spacing of the graphite flakes has been expanded, okay, expanded by the oxidations using strong chemical. So now we know that, okay, now we know that 6 hours is considered sufficient enough, because 6 hours is after 6 hours, this strong and intense crystalline peaks of graphite flake is gone. Okay, so the student choose 6 hours as the sample to conduct further exfoliations using mechanical approach to produce graphene. Okay, to produce graphene. So this is the result. Okay, so we check under TM. So it is very thin. Okay, consider as thin because you can see the electron kind of can pass through. And you can see that the image is quite transparent. Although TM is not something you can say transparent, but I think means the electron can pass through, okay, because of the thin layer of graphene oxide. So the sample stays stable, okay, stays stable long time. And then we check using AFM. The thickness is around 1.7 nanometer. So 1.7 nanometer is consider not really one layer, but maybe few layers of graphene oxide. Okay, so this is one example. I want to show you how can you utilize XRD as a tool to extract, okay, to extract information. For example, like in this case, we expand the graphite, highly crystalline graphite, into amorphous, okay, into amorphous graphite, graphite oxide because of the oxidation. Okay, so and we even run the final product, okay, using XRD, and it shows that the graphene oxide is highly crystalline. Okay, highly crystalline even after exfoliations and oxidations. Okay, so in this case, we just to use XRD to prove to make discussions, and another one is to choose what parameter for you to use for next experiment. In this case, we have different stages: graphite oxide. Okay, we don't know at which time actually we should collect the graphite oxide to do exfoliations. So XRD help us to tell us to choose. I think 6 hours would be the one, because there is no more intense peak, okay, for the graphite. Okay, so that is another example about polymer and polymer nanocomposite. Let's move on to average crystallite size. Before that, maybe I should ask any questions. I just talking, maybe student don't understand or any questions from the participant? If no, maybe I can just continue. Okay, so besides crystallinity, percent of degree of crystallinity, and besides knowing the D spacing, lattice parameter, okay, and also plane mirror index plane identifications, XRD can also tells you estimate crystallite size, okay, crystallite size of your material. So as I told you at the beginning, many materials we are dealing with in our daily life are, if they are crystalline material, there should be polycrystalline. Means that the material contains a lot of many small crystals, okay, combined together to form the bulk final material. Okay, so XRD can tell you what is the average size of crystals, okay, average size of crystal in your sample. So it is just an estimation, okay, just estimation. So this figure, okay, you have one particle, it can be maybe nanoparticle or micron size particle, okay, but what makes up of this particle actually is many crystalline, small crystal, many crystalline, okay, small particle, actually crystalline particle inside. So XRD estimate this crystalline size, not the particle size. You should be bear in mind, okay? XRD tells you the crystalline size, not the particle size, okay? Particle size you should use, let's say if the particle size is big enough, you can use optical microscope. If the particle is small, then you use TM or SEM, or you can even use dynamic light scattering, okay, or zeta sizer, okay, those particle analyzer that can tell you the particle size. So don't confuse, don't mix up particle size and crystalline size. One particle may contain many crystallites, okay, many crystallites inside. So it can be from nano range to micron, okay. So really depends, okay, really depends. But XRD can only estimate size down to nano, okay. If the crystallite size is in micron size, then XRD is not the right tools for you. Okay, so the formula that we can use is a scalar formula. Okay, scalar formula. This is the one simplified one. Okay, you can check. You can always find books. Okay, books. They are more complicated scalar formula. This is the most simplest method, but when you convert something from complicated to simplest, you will lose some sensitivity. You will lose some kind of resolutions. That's why scalar formula is just one very rough tool for you to estimate the size of crystal in your sample. Okay, so what is the formula? The size, crystallite size, equals to K. K is the constant, the scalar constant. We always use 0.9 or 0.94. It really depends. Some articles, some study, they use 0.9. Some people use 0.94. I think not so important because it's not even, it's just 0.04. Okay, lambda is the wavelength of the X-ray that you use. If you use copper, then it should be 1.54 nanometer. Then B, okay, B is the one key parameter that you should know how to extract. B is the full width at half maximum of that particular peak. Let's say you have 5 peaks. All the peaks can be used to estimate the crystallite size. Okay, but most of the time also, mostly people will use the most intense peak to do the calculations. But in the right way, you should use all and you average it. Okay, but it really depends. It really depends because, as I say, it's just estimations. Okay, it's just estimation. So B is full width at half maximum. This is the intense peak. Maximum is here. So half maximum, 50% of the intensity. You take the full width. Okay, you take the full width. You can check here and here. Okay, you take the reading of the 2 theta, but the theta, the length of this, the width should be in radian. You should convert from degree to radian. Okay, you convert from degree to radian. And theta is the diffraction angle. Okay, the 2 theta. So also in radian. Okay, also in radian. Bear in mind, this is important. Okay, so means that from this equation, you should know that the broader, okay, the broader the peak, the smaller the crystallite size. Okay, because of this. Okay, the beta. So the broader, the bigger the width, the smaller the crystallite. Okay, so it is important to note that square formula assume that crystallite size is smaller than the size of the X-ray beam. This is why I say just now, if the size, the estimated size is larger than the wavelength of the X-ray, then it's no longer is not correct actually. Okay, and crystallite size are randomly oriented. So essentially it's a wide distribution. The actual something like this, you see, you have big and small crystallite, but XRD only tells you the average size of it. Okay, so if the crystallite size is below 100 nanometer, is still considered okay, you can use it. Okay, but it's larger than 200, then XRD and square formula is not the right equation for you to use. Okay, further explanations. What is the procedure? You can watch this video. I think no point for me to do redundant work. To show you the video, then explain again. You can just watch it. Okay, and this video they use Origin. And Origin is very powerful tool for you to use for this estimation, because Origin can once you do the peak identifications, then directly the program will tells you the beta, okay, the full width at half maximum of each peaks, okay, each peaks. Very convenient way, very convenient. So what are the procedures? Number one, you collect data, then you identify, okay, you identify the peaks, as I say just now. If you have, let's say for instance like this one, maybe allow me to go back, this one. Let's say you have one, this is not enough. Let me go to the previous one, maybe. Okay, this one, 1, 2, 3, and 4, maybe. Okay, then you can identify the peak. Then you measure the full width at half maximum. Okay, then you convert the degree into radian. Okay, then you calculate the crystallite size. So you repeat this for other peaks. You can, let's say you have 4 or 3, up to you. Then you do the same calculations using the parameter obtained from that particular peak. Then you get the reading. Then you average the result. Okay, you average it. Then that should be the average crystallite size representing the whole sample. Okay, so bear in mind, square formula gives average, which may vary from actual size. It's very rough estimations, and it assumes that the crystallite size is smaller than the actual beam. Okay, so always have to remember, it's not a formula that you can use for everything. Okay, so why crystallite size is important? Because it determines your material properties. Okay, and the smaller the crystallite material, okay, the brittle the material. So this is important in engineering material, whereby you need strength. Okay, whereby you need strength. That's why if you remember, when people are producing strong sword or knife, they will hit and they will strike. They will hit, okay, using hammer. Okay, while the knife is still hot. So why? Because they will break the structures. Okay, they break structure and to promote formation of bigger crystals, okay, or smaller crystal combined with big crystal, okay, smaller crystal and smaller crystallite combined with big crystallite, that will give you strength. And crystallite size also important for you to optimize the processing, especially when you are dealing with process optimizations. Okay, so you know which condition give you bigger and which condition give you smaller. And crystallize is also important for microstructures. Okay, as you remember the first at the beginning, I showed you the microstructures of metal. Then you can see the crystals, the grains in microscope specimen. Then reactivity, you're talking about catalytic material, catalyst or chemical reactions. The material should be higher in terms of surface area. So the smaller the crystallite, the bigger the surface area, then the better, the higher the reactivity. And it's also important in quality control. Okay, for instance, like in polymer manufacturing, in pharmaceutical, okay, in semiconductor. So this is a very straightforward, very easy, okay, very easy method. Just run sample, then you have the spectrum, have the diagram, then you estimate the crystallite size. Okay, these are one example on catalyst. Okay, produce platinum. Okay, platinum catalyst. Then you can see the size. The size is different at different parameter, and also the XRD. So you can directly take the peak, then to estimate the crystallite size. Okay, so this is another study done in also long time ago, 12 years, 13 years ago, okay, by I think our research group. So in this work we produce we try to synthesize cobalt ferrite, cobalt iron oxide or cobalt ferrite, okay, nanocrystals. So we would like to know how much the size of the particle and the crystallinity influenced the magnetic properties of cobalt ferrite. So what we did is we conducted the synthesis process from by mixing the precursor, cobalt salt and ferric salt, and mixed with sodium hydroxide, the caustic. Then you get an intermediate mixture, and you put into hydrothermal autoclave, and you heat it up to different temperature. And to adjust the crystallinity and also the size of the crystal, we even conducted post heat treatment, because heat can promote crystal growth. So you will have bigger crystal, so and also better crystallinity. So to increase the number of specimen we have, number of sample we have to study wider range of crystallite size, we conduct calcination heat treatment up to 1,200 degrees C. So these are the sample that we managed to produce with different crystallite size, okay, and different intensity in terms of the peak. So here's the peak. So the XRD result. So this is the one we do hydrothermal, and these are post heat treatment calcinations. So by combining these two processes, we managed to collect a series of samples with different crystallite size. Okay, so this is the peak that we use to estimate the crystallite size. Okay, and we observe under the ATM, you can see the size of the particle is bigger. So particle size doesn't mean big particle size doesn't mean small, bigger crystallite also, because one particle can contain a lot of crystals inside. Okay, then we study the effects towards the magnetic properties, and indeed, the bigger the crystallite size, the better the magnetic properties of the nanoparticle. So this is another example of I included here. to explain why XRD is important. Okay, why XRD is important and can be used for your study. Okay, so yep. I think I think I finished quite fast also. Never mind. Maybe I can spare the time for discussion later. Okay. So, but I can conclude now. It's okay. Then we can proceed for Q&A, or maybe I can try to search more related work if you think it's necessary. So, as a conclusion, XRD provides you information in terms of crystal structures. I think this is something no doubt. This is the most straightforward method. I think the best method that you can use, besides others, for instance, like optical microscope, is not possible for you to get the crystal structures. So this is why XRD is popular. Then it can tell you unknown materials inside your materials. For instance, like you have completely new material you synthesize. You don't know what kind of material should be contained inside your sample. Then you run XRD, you feed with the library or database, then you should get the result. You should able to identify what are the materials inside the sample. Then it provides information about quality. Okay, so how well the material been crystallized, or whether you have defects, or you have any strain, residual strains or residual stress. And another good characteristic is XRD is non-destructive method. Okay, the sample can be collected back and be used for other analysis. Okay, and also the testing conditions will not destroy your sample. It's not like SEM or TEM that when you analyze the sample in the vacuum chamber, your material actually exposed to vacuum and it may change the properties, okay, during the analysis, but XRD is fine. So it has a wide range of applications, many different materials. Okay, it's also possible for you to run using XRD. Okay, so that is the content I can share for this topic. If you have any questions, I have other slides actually. I can go through maybe after the Q&A and also the outbreak.
Prof, thank you so much for your presentation. Especially for me, it's special, but other students, they may not same field, because you know our faculty environment, so we have multidisciplinary student. But by the way, I can see actually lots of different knowledge and also deep knowledge, because I know the XRD, but I never get like how to enter the deep analysis. So when you discuss about that, that's why today I'm trying to focus on your lecture, and I can see that which way actually I should analyze the XRD, the materials or crystal structure, because there are lots of things. Just only XRD we can focus many things, and that can also change the material structure or quality. We can if we do the deep analysis, like how can we go to the website source, and we can compare, we can change the data, and also the using origin. So it's all things new for me. I just know the fundamental or just analysis, follow up someone, but it's very new for me. I think that is new knowledge, and yeah, we will share in our university group for especially for the analysis.
Yeah, I actually would like to demonstrate using Origin to do the deconvolution, but unfortunately, I could not install the Origin in my computer here. So if I can do it, then I can maybe guide step by step. But after I and also I also think of if there is some video that student can also refer, then might as well be student can directly go to the video, right? That's why I provide the links here. So maybe you can the student can go through and repeat again if they have the software, right? So that should be quite useful also. Yeah.
Yeah.
And a lot of work that you need to that need to assisted by the software. For instance, like uh the plotting, okay, using origin, then to do the fitting, to do the data collections, the standard sample, how to do the plotting, all will require a lot of training practice for you to able to get
And
good image.
you share the some recommend the some website
Mm-hmm.
material studio, right?
Yes.
Material studio and free software, the COD. So here we can see that we can change the data, right? In the
Yep.
website, this how we download the file, we can change the open the file, and then we can change the data, like what we get, we can put our data also, right?
Yep, you can do matching also using that. So a lot of fine tuning, or maybe a lot of other things you can do. One thing to maybe to identify what kind of material you are dealing with, then and you can refine the searching, because if you really look carefully, like the one I showed you just now, this one, if you notice, there are many, you see, so many, even with so many, so refined. So you have to really careful when you choose the CIF file. So, and this is one disadvantage, but also advantage. Means there are a lot of possibility that you can play around. Yes. So I didn't really explore very deep in using this database, but I believe there must be more thing you can get from here. So but just need time. Just need time to play around, especially the students.
Yeah, yes, bro. But I think that this is the like fundamental concept, and when we do the step by step, and we learn more, because we now we do the website, and then when you do the our own calculation, then and also another software, you show Vista software, right, bro?
Yes, yes. Vista software, yes.
So we can open the file, CIF file by Vista software.
Yeah, very. This is quite useful. So I didn't know this actually. I just recently find, because I do not have the access of the Material Studio and also the license database. So I try to ask around, then I try to search. Actually there are a lot of open database that you can download. Then people are sharing also. So you can even go to ResearchGate, and you can open up questions and ask people whether they have the JCPDS card of the compound that you want. Then people are kind enough, they will share the JCPDS. The most convenient, I think, would be the JCPDS. If you can able to get the JCPDS card like this, then it will be more straightforward. But I like the Vesta, because Vesta can offer you other tool as a tools for you to draw, for you to play around. Then I like this software actually. Yeah. So you can student can go to this link. I think this
Probably you can share maybe.
Yep, I'll convert it into PDF, and I'll share you the slide. Then you can share with the students. Yes.
Okay, Prof. And
Yes.
Prof, I think that now we don't have, I don't have any question. I just know about this. So if you allow me, maybe we can go for break.
Yes, yes.
And we'll back again in Thailand time, 1 p.m.
Yes. And also later I will share maybe a little bit of XRF, because actually I send by some notes on XRF, because I foresee I may talk very fast.
It will be better, because if you show us that, because sometimes we confuse XRF and XRD.
Yep. Yeah, so that's the purpose I included the SRF slide in my presentation. So just want to make sure that don't confuse, because many students confuse, even my student also, some of my undergraduate students, they confuse about XRF and XRD. They thought XRD can tells you chemical compositions, just one alphabet difference, right? So I will explain. I will share XRF later.
And if you have some time, maybe you can discuss also the contamination, like when we the synthesis the sample, sometime the why it what should we do for in that case to how
Okay.
to get our sample. Yes, bro.
Sure. Sure.
Okay, bro. So
Thank you.
we'll back again 1 p.m. Okay, bro.
Yep.
Thank you, bro.
Thank you. Thank you very much. Thank you.
Hello, Prof. Welcome back again.
Yes. So,
Okay, so we can proceed for next session, Prof.
sure. I will share my screen.
Okay, Prof.
Okay, can you see my PowerPoint?
Yes, Prof. We can see your PowerPoint.
Okay, good. So let's continue. So hope everyone have good lunch and rest. So we have another 1 hour. So I have included as advised by Mr. Sarah just now. So maybe I can add a little bit of information about how to prepare a sample in detail. Actually, I have the information this slide before this, but I just keep it. I thought this is something will take quite a long time. So, but eventually I still have time, so I will just explain a little bit. So, when you send a sample to XRD, you always have to remember, always have to be careful in terms of the sample, the size of the sample, in terms of the let's say you send a powdery sample or some particle sample. If the particle is big in terms of the size, then you may have a problem in terms of the compactness of the specimen that put onto the SRD holder. So just imagine this is your sample at this size. If you put it into the holder, then you may have a lot of air pocket, air cavity that may reduce the signal to noise ratio. So size of sample is one key factor. First thing is if the size is big, then just imagine this is the one of the big particle of the specimen. Then if you have three important plane, the HKL, the Miller index plane that you want to observe. So you try to imagine if this is the size that you have, which is big, and you may reduce the chances of the three planes to be detected by the X-ray XRD. So if you grind this particle, a big particle, into smaller size, so you actually increase the chances of this plane to deflect the X-ray. Right. First thing, you increase the chance, the possibility. Okay. Second, you reduce the air pocket. Imagine this is the particle. This is a sample, and you have air pocket, empty space. So this empty space will not actually contribute to the diffraction. So means that by grinding big particle into small particle, you can increase the compactness of the sample inside the sample holder. Okay, first compactness, so increase the chances, increase the sample size, sample amount of sample. Second, reduce the air pocket inside the sample. Okay, so total randomness of crystal orientation is one important. Okay, so how random actually is the planes that you want to detect, the HKL plane. So just imagine if this is the sample compartment, then you have three big particles sitting inside here. You just try to replace this into here, then you have three or four big particles inside here. So you see the arrangement of the randomness of the crystal plane is just happen at three or four particles. So if you grind this into, let's say, 4 or 10, so you increase the randomness of the planes inside the sample holder. Okay. Second, sufficient number of chrysolite to get representative intensity distribution over the sample. So you increase the number of chrysolite size, okay, that will get exposed to the X-ray. And last one, if you increase the chrysolite size, so you increase the number of chrysolites, then you have sufficient intensity of the diffractions. So this is one very important factors to take care before you send your sample. So here are, I think I got this from this website. You can just check. They prepare a good report on this. So they compare one with well-ground sample, another one is underground, means the sample is bigger in size. So the red color one, you see, the intensity, look at the intensity of the diffractions. It differ a lot. You see, one is with CPS count of 50,000 without grinding, not even 10,000. So I think this information actually even bring up another more important message, which is if you have, let's say, 4 samples in your study, you try to study different parameter, let's say heating or thermal treatment on your sample, and you have four samples with 4 different specimens. If the specimen are not in the same size, one is like this, one is like this. Okay, even the same sample already give you different intensity. What about the parameter that you study? So it may mislead you, it may give you wrong information. You thought that sample A is high intensity, sample B is low intensity. Then you say, okay, sample A is better crystallinity. But you may be wrong. You may be wrong because if you do not prepare the sample in a control size, then the size would be one of the factors that give you wrong message. Okay, so this should be taken into the consideration. Okay, you really need to be careful. I think this kind of yes.
I have a question. So that means that we should be more careful even we grind, and we should be more careful about the size, because due to the size we may follow the wrong direction, right?
Yes, you're right, Mr. Sarya. And actually, to be more precise or to be more control, you should also sieve your sample, not just grind. You need to sieve it up to collect the sample at with certain range of size. So means that to sieve at 2 different mesh, then you collect the size of the particle at in between 2 size. So that would be much better. Yeah. So this is one very important thing, because I think some of my students maybe also make the same mistake also, and so really need to be careful. This is one of the precautions. So, but grinding also may lead you to somewhere else. Under grinding, you have problem. Over grinding, you have also another problem. So I think it's always about experience, and you need to really practice and repeat maybe. So this table actually from the same website. They encourage from this table, that means that they encourage us to produce the sample at about 40 micron. So in 2 digit of micrometer range. If under grinding, then you have like I mentioned just now, you may have insufficient crystallite, so the signal will be very low in terms of intensity. But if you do it over grinding, then you have also problem. You may destroy the crystallite. Okay, you may destroy the crystallite. So if you should remember the previous slide, we use scalar formula to calculate or to estimate the crystallite size. But if you do conduct grinding, over grinding, then you may destroy the crystallite. Then the result, the reading, the crystallite size that you estimated may be wrong. Okay, and also you may also induce lattice strain. Strain is a defect actually inside your crystallite. So have to do it carefully. Okay, then if you do it, you overgrind it. Okay, overgrind it, then you may have some. Let's say we know that grinding introduce heat. Heat will maybe you grind in the normal atmosphere with oxygen in the atmosphere. You may have oxidations. So oxidation is defect actually created. You create amorphous. So you may reduce the crystallinity of your sample if you overgrind it. And tools that you use to do grinding is also very important. You have to use proper one, okay, mortar or maybe stainless steel ball mill, okay, then to make sure that no contaminations onto your sample during you do when you're performing grinding. Then amorphizations, same thing. The crystalline convert into amorphous if you do overground it. So is you just need to get a balance. Maybe from the naked eyes, I believe you're able to decide when to stop. Then even better, after grinding, you do sieving. Okay, you use certain mesh. Okay, certain mesh then to collect the sample, the specimen at a certain range of size. Okay, so another precaution is sample orientation, especially when you have one-dimension material or two-dimension material, flat material, for instance, like fiber, blades, okay, tabular or platy in the plate form sample. I give you an example like natural fiber. Okay, that would be laying on the on top of the sample holder. So you will have certain orientations preset inside the sample holder. So that is also another issue. So when the sample crystallites do not randomly orientate because of texture of or because of the physical geometry or texture or the physical or the shapes of it. So this happened to something like this. They say you have a rod size, then you see this rod will sitting flat on top of the sample holder. So the crystal plane no longer random, because XRD always require high randomness of your specimen. So if your sample is sitting like this, then eventually all the crystal plane will be preset, pre-aligned inside your sample holder, and those other crystal plane will be. I think this is not fair, right? Because you already have the bias. This red color crystal plane is perpendicular to your X-ray, so means that the expose of X-ray no longer random enough. Then eventually you will have poor quality of diffractions happen. So this is example given by this author. Okay, prefer orientations and prefer orientation. You see, completely different intensity ratio between the diffraction speed. So you see, preferred one like this. Okay, the red color plane give you the higher signal, definitely, because red color is the most exposed. Then if you have no preferred one, the blue color planes and red color plane will be randomly or aligned, okay, aligned inside the orientated inside the sample holder. So this is another precautions. So one example of this should be like natural fiber. So like paper, let's say you have a thin sheet of paper. So the fiber is aligned, is actually laying on the slipping, like it's just laying on top of the sample holder. Then the crystal plane already pre-oriented. Okay, it's not randomly. So what you need to do, you need to grind it. You need to grind the natural fiber or the paper sheet into powder form. Then you press the powder into a compact manner. Why you need to press it? Because without pressing, you will have a lot of air pocket. So the air pocket will actually reduce the signal to noise ratio of your result. So this is also one precautions. Okay, so I think for sample preparation, normally we will talk about because XRD you can only run for solid sample. So solid sample definitely there are powder or some rock sample, big particle, small particle. So in terms of precaution, these two will be the most important. Besides those, I mentioned, I don't tell you just now, size of the how much sample amount they're putting in into the sample holder. Okay, then sample alignment. So background correction and standard sample, all these are be done by the technician. So these two will be the most important, the important one. Sample preparation, and so how much sample you put into the sample holder. That is for XRD. Okay, so let's move on to XRF, as I promised just now. So Mr. Sharia also mentioned just now. Some students confused about XRD and SRF. So the name X-ray, okay, and XR diffraction. Another one is fluorescence. Okay, fluorescence. So let's give you an example. This is one example of incandescence. It's something like fluorescence, but not because of X-ray, but this is because by heat. So when you burn, okay, when you heat up a steel bar using fire, so the steel bar will receive heat energy. Okay, steel bar will receive heat energy, so energy will be accumulated by the sample. So when you remove it from the fire, then the heated steel bar will slowly release the thermal energy wave in terms of incandescence. Okay, same thing go to material, any metal exposed to X-ray. The energy of the X-ray will excite the material. Okay, same like fire excite the steel bar. So the steel bar release the energy in terms of color. Okay, sorry, for photon. Okay, photon. This is thermal wave photon. So most probably it's infrared, but this one in X-ray fluorescence, energy absorbed by the metal atom and released in the form of fluorescence. Okay, fluorescence will be, sorry, this is the X-ray. Okay, X-ray tube supply the X-ray, and the energy of X-ray excite the atom, okay, and electron, and the atom release the energy in the form of fluorescence. So, and the fluorescence signal is a fingerprint for different element. That is the very straightforward, the basic of XRF. Different matter, okay, different atom, okay, different element will have different number of proton and electron. So that will give them special characteristics to differentiate from other atoms. Okay, that is their fingerprint. So when atom excite by X-ray, okay, because of high energy, X-ray contain high energy, so the energy will excite the electron. Okay, excite electron will be escaped from the energy shell. Then the energy shell, the empty spot will be replaced by electron from higher energy level, and this transition from high energy level to low energy level will be released in the form of fluorescence. So because of different atoms have different binding energy to the surrounding electron, so the fluorescence release, okay, the fluorescence that release will have specific energy value to represent every single element or atom. So that is XRF, concept of XRF. Okay, so there are different kinds of products in the market for XRF. You have very powerful one, okay, very expensive, few hundred thousand of ringgit Malaysia. So big one, medium one, benchtop, and handheld. Okay, you can have also handheld SRF. So as I told you just now, different atom, different fluorescent energy. So that is your fingerprint. So you carry this handheld machine, you go to the field, you go to the any site, then you can just strike the X-ray on the surface of the specific material, even the pipeline, a building, any material, without taking specimen, you can directly strike it on the surface of the material, buildings or pipe, piping or pipeline, okay, or soil sample, okay, then immediately you can get the reading of how many percent of element, this element A, how many percent, element B, what is the percentage. So this is XRF. Very convenient, okay? You have handheld XRF, but you never have handheld XRD, okay? Why? Because XRD require very sophisticated or very nice alignment in terms of the X-ray path in order to get the diffractions, okay? The diffraction is the key, it's a, sorry, it's a key process in XRD. So that diffraction require very good alignment in terms of the sample holder, X-ray source, and also the detector. That's why we do not have handheld XRD. But XRF we have. Okay, so XRF is an analytical tool. Okay, very common. Okay, very common. Any field, you can have it in steel making plant, plastic industry, okay, wastewater plant, whatever. Okay, food industry, they want to detect any contaminants, they say heavy metal contaminant inside their food, they can just test, okay, using either handheld or using lab XRF. So the function is to determine chemical composition. So what is chemical composition? Element. So it's elemental composition. Okay, sample can be solid. Yes.
One question, like XRF only can detect solid material, right?
No, liquid also can.
So that means, so how can we define, like we know the ICP-MS, or they also detect the heavy metal. So, or
yes.
ICP only detect only few amount of metal, not all, right?
Yes.
A specific.
Yep, but XRF can detect even wider.
Okay.
Even wider, but the sensitivity of SRF is not as good as ICP. ICP and mass you can detect down to part per billion, but XRF 1 or 2 digit of 2 decimal, 1 or 2 decimal of percentage only. So they meant for different purposes. Yes.
Okay.
Yes. Good question, Mr. Shara. ICP made more for trace element. If you have part per million or part per billion, then you need ICP. But if you are dealing with something like, let's say, soil sample, then, or maybe your raw material, then you can use it. You can use it.
For organic material, we use NMR, right, Prof?
Yes, organic material we use NMR, but NMR is meant more on the molecular compound, how it you can predict, you can use NMR result to predict molecular arrangement functional group, whether it is sitting at the alkene, the aliphatic backbone, or the N group. That is for NMR. Okay. Yes. Okay. And another elemental, another instrument for elemental composition analysis is CH and S. Carbon, hydrogen, nitrogen, and sulfur. But that is very special for only these few elements. Yep. Yeah.
Thank you.
Okay. Yes. So SRF can be used for solid and also liquid and powder, and even filtered. Okay, filtered also can. So determine thickness, thickness and composition of layer of coating can also be done, but requires special calibration before you do it. Okay, then it is known as fast, accurate, and non-destructive. Why fast? Because you just strike it. You have a handheld XRF. You just get contact like this one. Let it contact with the surface. You just press a button. Within few seconds, then you have the reading. Very fast process. Okay, and minimum sample preparation is not like ICP.
What is the difference between, like, we can see that the big size of XRF and also small size. There's a difference between both
the convenience level of convenience. This one you can bring to any places. You can bring back your home. You can test your toilet. You can test your anything.
Is it same result?
No, sensitivity also different.
Okay.
The sensitivity will be dropped definitely. the detector used in handheld will be lower in terms of resolution, because they don't meant for this kind of application. They do not require this sensitivity, especially for hand carry, let's say in the
So
field.
from that means that the hand carry one we can use for the fundamental analysis, not more deep characterization, right?
Yes.
If you want
Yes.
deep characterization, then we need to do in the lab.
Yes, you're right. You're right. Yes. So this is for you try to imagine if you have if you are an engineer, you would like to check contamination of the, okay, let's say a pipeline been corroded after corrosions after some time, then you want to investigate the root cause. So the pipeline is in the industry and they're still in the productions. You cannot cut specimen from the pipeline, right, to bring back to your lab. So in that case, you need to bring the handheld one to test on the spot. Okay, so that's the purpose to have the handheld one. Okay, they serve for different purpose. Yeah. So very fast, accurate. Okay, and minimum sample preparation. So as I told you just now, no, not much. Something like XRD. Okay, something like XRD, not like ICP. Mr. Shara, if you remember, ICP require a lot of preparations. Okay, so suitable for metal, cement, oil, polymer, plastic, food industry. So even oil also can. Okay, so mining, mineralogy, geology, so environmental analysis of water, wastewater, waste material also can be used. So there are two different types of XRF. One is with the mode of energy dispersive. Another one is wavelength dispersive system. But I think I'll just explain in general. So what are the difference here is energy dispersive X system can only detect from sodium to uranium. But wavelength, okay, wavelength WD XRF can detect from beryllium down to uranium. So you have extra element that you can detect using wavelength dispersive system. Okay, so the concept behind, okay, the concept or basic of SRF is something like the X-ray cathode I explained to you this morning. When a electron, okay, electron strike, excite an electron, electron strike an electron, then electron at outer energy shell replace the position, then you have the X-ray. But in XRF, you are not using electron, you use X-ray. Okay, you use X-ray, then the X-ray excite the atom, okay, on the electron. Any electron will do actually, not only at the K shell. So L shell, M shell, and N shell will also happen at the same time. So we take the K shell electron as an example. So when electron with high energy excite atom, and electron at K shell will receive the energy and eject out from the atom. So it will be missing, gone missing. So what will happen is this empty position will be replaced by electron from outer shell. So for instance, like from L shell, then this is alpha. Okay, K alpha. Then if the electron is coming from the M shell, then it will be K beta. Okay, so this alpha beta, okay, will have specific energy value for different element, okay, for different atom. Means sodium, oxygen, carbon, copper, silver, all of the element in between beryllium to uranium, they will have their own fluorescent, okay, own fluorescent X-ray, okay, X-ray fluorescent wave detected by the detector, okay, at different energy value, okay, with different energy value. So different matter or different atom or different element will have a list of possible fluorescence wave. For instance, like oxygen, this number, Okay, so nitrogen, this will be the number. So very discrete. Okay, this is a very discrete number. So special for every single element. So that's why X-ray fluorescent XRF can detect many elements because each element will have their own X-ray fluorescence value. Okay, so why each number, each element or each atom have their own? Because we know electron actually is orbiting nucleus, and the energy level is quantized, right? So every atom will have their own electron energy level and very specific one. Okay, so there are no overlapping. So with this, you can differentiate. Okay, you can differentiate what type of atom from the fluorescent signal produced by this process. Okay, so that is the principle behind of SRF. Like I told you just now, the energy level is quantized. Okay, so because of the atomic number is different, so energy level will be also different. When the electron at the outer shell come down to replace the inner shell, that level, that energy, the amount of energy released in fluorescent, in term of fluorescent, will be very special. Only one, okay, or for one single types of atom or elements. Okay, that is XRF. I think this is the same. I think this is just redundant. Okay, just redundant. So I told you just now, K level, K shell, from L shell go down, we call it K alpha. From M shell, sorry, and from M shell to K, we call it K beta. Okay, same goes to, let's say, from this is KM. Okay, from from L shell to M shell, we call it L beta. Okay, so alpha and beta. Okay, only alpha and beta. So it depends on which the electron fall to which energy level. Okay, which cell. That's if K shell, we call it K alpha. If M, we call it M alpha, L alpha. Okay, so each fluorescence wave will have their own number. Okay, these are examples of spectrum. Okay, these are two examples of XRF spectrum you can obtain from your any sample which contain this type of element. This is very complicated. I think this would be an alloy sample. Okay, metallic sample contain chromium, selenite, zinc, copper, nickel, copper, iron. So many. So if you notice, you have more than one peak representing one metal, one element. For instance, like you have iron here and also another iron here. So red color arrow is K alpha. Green color is K beta. So this is very good because you can increase the number of reading, the chances of you to detect possible metal presented in your sample. Okay, so this is another example of spectrum from soil sample. Okay, from soil. Inside soil, you have this kind of element. Okay, again, you have calcium alpha, calcium beta. Okay, potassium alpha. Okay, then you have iron. Okay, iron beta, iron alpha. Okay, iron K alpha. So what? So means that the peak positions, the level, okay, the energy value of the fluorescence released give you the information about what kind of element. Okay, what kind of element? So again, the energy value determine elements. Okay, types of element. Okay, this is qualitative. At the same time, XRF can also perform quantitative from the peak height. So how many count? How many count of the fluorescence detected? Okay, for example, for iron. Okay, for this iron K beta. So let's say this is 1,000 count. I just give example. Let's say 1,000 count. Okay, the more count means the higher the concentration of it. So intensity tells you concentration of the element. So eventually, you have this kind of result. So this is, I'm not sure what is this result, this material, but you will get the reading in terms of compositions and percentage. So you have silica 99%. Okay, you have iron oxide 0.31%. So this could be, I think this would be a silica sample with some impurity inside. Okay, 0.31, 0.001%. So Mr. Shara, you asked me just now whether there's in terms of sensitivity. So now you can see it only down to part per million. Part per million, not like ICP, part per billion. Okay, so but it's more than enough actually for normal sample. Yeah, should be enough. Okay, so advantages of X-ray fluorescence XRF: rapid, very quick one. You press the handheld, especially the handheld one. Okay, non-destructive. The sample will not get destroyed. No spectrum. It's not like FTIR or NMR. You need to do data interpretations like XRD also. You need to match with the JCPDS cut. So that is very troublesome actually, but serve for different purposes. Okay, so no spectrum. Immediately you can get the table like this. And in paper, in thesis or in paper, we don't show this one actually. Even sometime technician will never give you this result, because it's meaningless. So they will directly give you a table, okay, in the result in table form, okay, and easily analysis, okay, because basically everything stored inside computer, then immediately you can tell you the concentration, and high accuracy, okay, from barium to uranium, easy qualitative, okay, and easy quantitative, and easier sample preparations. Okay, these are advantages of XRF. So in terms of sample preparations, it's more about the same like XRD, because basically these two analysis instruments deal with X-ray. Okay, so basically they are the same. Sample cleaning, make sure that, let's say you're bringing a handheld XRF to the site, then you want to measure on the surface of concrete. Make sure you clean the surface, remove dust, because especially sample or building exposed to atmosphere outdoor, it will be quite dirty. So you need to clean the surface first. Let's say the surface contaminated by wax or oil, then you need to remove it, or else the reading of carbon will be quite high. Okay, so, and second one, sample size reduction, like mirroring, grinding is also needed to increase the surface area, and also to increase the compactness. Okay, like this one, if your sample is quite big in size, you need to grind it, then to make sure that it fill up the whole sample holder. Okay, to maximize the reading. Okay, signal to noise ratio. And if your sample is not homogenized, let's say you have some mixture of powder, maybe here you have some coffee powder, here you have chocolate powder or some flour, make sure you mix them well, or else you may have inhomogeneous result. Okay, some composition may be higher in terms of the percentage. So you can mix it using mortar, pestle, or sample homogenizer. And sample need to be dry. Okay, if the sample is powder form, then it's contain a bit of water or moisture, then you can dry, like especially for dry sample. But water sample is fine. Okay, if wet sample is fine, liquid sample is fine. Okay, if you want even better to increase the compactness of your sample inside the sample holder, you can consider to pelletize it. Okay, you can use pelletizer and mix with a little bit of binder, some kind of, like, let's say wax, polymer binder, boric acid, or cellulose. Okay, pure one, low contamination, to mean very less contamination, impurity one. Then you use it as binder to increase the strength of the pellet before you send the sample. So after you press, the sample will become pelletized. Then only you send your sample to XRF. So all the sample will be prepared using the same procedure. Then when you send, everything will all the sample will be consistent in terms of the sample preparation. Try to imagine if you pass your sample, let's say you have 4 samples, if you pass sample in the container, a vial, then you just give to the technician or the operator. Then if he did not prepare a sample nicely or consistently, then some sample may be higher intensity, some sample may be lower in terms of the compactness, then you may have misleading result. So this is also another precaution you can take if you want to really control the quality of the result that you want to get. Okay. So I think that's all for XRF. Yeah, I think not much. I don't explain much on this one. I think this should be not so important because most of the time, in university we will have the wavelength dispersive system that able to analyze from barium, okay, to uranium. This is, I think, maybe not so popular now. Mostly this is the mode, okay, but the working principle is more or less the same. Okay. Okay, I think that's all from me for today, Mr. Sarah, and also everyone. So I hope you got something. So thank you, and Mr. Pisa Hajima back to the class. Okay, no problem.
Thank you so much, Prof. So if you have any question, please feel free to ask.
So if no question, also no problem. No problem. I will. You can email me if you want. If you have question, no problem. I will share the slide to Mr. Sarah so you can circulate.
Linda, are you available? Linda. Yes, I think you can see some idea about in terms of not all from XRD, because we have still have 10 minutes. So she actually wants to know the qualification exam for PhD.
Oh, qualifications. What do you think? What is that? What do you mean? Qualification means to become a.
Some university, for example, our university, Prof, they have QE exam before proposal defense. So, or how can focus on the specific research, because she is right now she is a bit struggling on that. So if you could give some guidance.
So what do you mean by QE exam, Mr.
In our university, we have the QE exam for qualification before proposal.
Oh, okay. I see. Oh, this is quite special because I thought because from my understanding, all university they offer master and PhD courses program. Then the requirement should be already fixed and predetermined before, I think, and they also publish it in the website already. Yeah. So, and why did the university require the examination?
I think I don't know actually the graduate skill is still there, but I have seen some university, even others country. First of all, they doesn't have that kind of things, but still Thailand they have.
I see. So what kind of subject they will test, they will ask you to answer during the examination? What kind of questions?
Let's discuss about what kind of research you want to do and why you focus on this, something like that.
I see. Okay, now I understand. So it's meant more on to know how well the student is prepared. Yeah. Okay.
For research, yes.
Yep. So if that's the case, then my advice would be you need to show them your seriousness, how keen actually you want to continue your study and how well you understand the topic that you want to do. Yep. And it always, I think it again goes back to the proposal that you prepare, then I think the test is mainly to make sure that the student is ready. I think that should be the purpose.
Okay.
Yeah.
Thank
So
you, Prof.
Linda is not a Thailand student, right?
No, she's from Philippines, but she's working in Thailand, and her
see.
field is social science.
I see. So yeah. So I'm not sure whether Rita has the topic, research topic already or not. If yes, then just do preparations, read more, and try to understand. Then try to stand by lah. Any question they will ask you.
Thank you, Prof. Thank you. I think
No
we
problem.
are end of our session, and from audience now don't have any question. So thank you so much for Prof for your time, and we look forward to your next session on 24.
Yep. Thank you.
Okay.
Thank you very much. Thank you, everyone. Thank you, Mr. Thank you. See you.
Thank you.
Bye
See
bye.
you, Prof.
See you.
Bye bye.